So we've talked a lot about vector data so far, and here in Unit 7, we're going to start talking more about raster data and the types of raster data we bring into GIS, typically bring into GIS. So quick rehash of what raster data is. You've heard about this at least twice now, but let's do one last review before we jump into the different types of remote sensing that we can bring into GIS. So what is raster data? Again, it uses a grid of equal sized cells to cover an area of space. So the value in each cell corresponds to the characteristics across that cell in its location on the Earth, the spatial phenomenon at that particular location. So imagine draping a 10 by 10 meter net, so to speak, over your property, right? Some of those squares would have fall on where the building, where your house is. Some would fall on where the driveway is. Some would be the yard, trees, etc. So we would be basically generalizing that area based on what the predominant characteristic was within each of those 10 by 10 foot or 10 by 10 meter squares. It's ideal to represent that for data such as elevation, slope, temperature, rainfall, wind speed, because these things don't have a distinct shape like a parking lot or a building or something like that would have. Um, they don't necessarily have such a vast change in the measurable values across that grid square, so it doesn't change dramatically across, say, a 10 by 10 foot square. And they're also not abrupt, like vegetation type going from grass to water, for example, is a nice sharp line. And it's hard to represent that if that line falls right in the middle of one of your grid squares, because then how do you decide which value that particular grid square gets. And if you're 10 meters by 10 meters and the line's right down the middle, then it's half and half, and you're off by 5 meters in determining where exactly the extent of that spatial phenomenon is. So raster data has some challenges for sure, but it's also really good for these non-distinct shaped features, again, like elevation, temperature, rainfall, slope, etc. Represents continuous surface. You divide the data into rows and columns. And this is really useful when you're kind of overlaying lots of raster data sets on top of each other. The origin in this particular case is usually the top left. So if you notice how this numbering is 1, 2, 3, 4 for the columns, 1, 2, 3, 4 for the rows, very similar to the way a spreadsheet would be. And so the coordinate pair, or this grid cell pair for the top left, is 1, 1, and so on and so forth. Rows as y coordinates and rows as x coordinates, and each cell is explicitly defined by its row and column position. So over here we have column 3, row 2. It's 2, comma 3. That's how we're defining it. And each cell has its size, right? In the x-axis and in the y-axis, what is the dimension? And these are uniform. If it's 10 meters by 10 meters or 5 meters by 5 meters, they're always perfect squares. So here's another example of what I was trying to describe earlier. You've got a beach, grass, forested area, and water, where in reality it looks like this, with very clear, discrete locations for the edge of sand and the water, where trees and grass come in. And raster has to generalize that across the entire grid scale. So imagine again that you're taking that net or the grid and overlaying it on top of the real world, and this is what you end up with, when in reality it really looks like this. But there are times when that's totally fine, that it's for analysis purposes, this is really well, works really well. So let's take a look at some of those advantages and disadvantages. For raster data, certainly the data structure is easy, right? It's got a row and column number. That's it. It's compatible with remotely sensed or scanned data. Any sort of raster-based scan or image works really well. And you can do real simple spatial analysis because you're simply overlaying grids. And you don't have these complex lines that may partially cover certain areas. Now, of course, raster data actually does take a lot more storage space on the computer. The resolution has a function of that. Trying to take it from one projection to another is more difficult because you don't have finite locations. You have these grid squares that you have to distort when you run projections. And it is difficult to represent topological relationships, that area definition, connectivity, etc., because sometimes the raster cells don't always stay continuous. For example, if you imagine back here in this previous slide that we had a river running through here, well, we may only indicate that there's a river there where it is the predominant portion of one of the grid cells. Otherwise, it may actually disappear and come and go. So that has a lot to do with resolution, of course, but it is a problem. And then vector data, of course, less disk storage space. You can have these relationships that are easily defined, and it's easy to create output that looks like a real map. But it's got a complex data structure, not really compatible with remotely sensed data, the way that images are captured. Software and hardware is often more expensive to manage and manipulate vector data. Analysis procedures can be difficult, and the overlaying vector maps is time consuming because they're not nice clean grid squares, they're complex shapes and lines. Within the raster data model, you have cell values. Each cell, right, each one of those grid squares carries a value, represents the characteristic of the phenomenon on the ground at that location. Coding for those values can be a straight number or a decimal place, which is what floating point floating point indicates. An integer, as you see here, no decimal digits. A floating point has decimal digits. The integer usually represents categorical data, right, which is grass or water or sand, for example, so 1, 2, 3, or 4. And a floating point represents continuous information, which might be the elevation of 10.5 meters, 10.3 meters, for example. So you need to represent the average across that grid cell. The floating point or decimal place raster requires obviously more memory because you've got to have all those extra digits in there. And it is an important factor when depending on what kind of coverage of the area you need. Integer values can be accessed through an attribute table. The floating points don't have an attribute table because there's a really large number of records. Can you imagine if you're looking at 1 to 100 integer, that's just 100 values. 1 to 100 with 2 decimal places is getting into thousands and thousands of potential values. And so we usually don't store that as an attribute. You store it on a range. And you'll see that when you work with some of this geospatial data. Cell value of these raster data sets typically applies to what was most common in the center of that cell. And in some form of distance measurement is done to determine what the average is across the cell. So many of the operations that we use with data sets are based on the entire cell value instead of the points within a cell. So basically you assume that whatever that average was or what was ever in the center of the cell applies to the entire cell. And that's a problem because if we look back up here at our diagram, look at the beach here, right? Part of that beach was probably water cutting in, but it had to generalize it. Even up here, we've got a nice smooth curved surface. A good portion of the cell was probably still grass, but because most of it was sand, it comes out in a blocky shape like this. So the value had to be applied to the entire cell, and that's sometimes a downside. Again, the size of the cell determines resolution. A 10 meter by 10 meter, that's 30 some feet by 30 some feet. On the ground, you may have lots of different variation in there. But if you do a cell size of 6 inches by 6 inches, as is the case with a lot of low altitude aerial photography, you can make out quite a bit of detail. So the cell 6 inches by 6 inches is a much higher resolution than a cell that might be 10 meters by 10 meters. So a large cell size, right, 10 meters by 10 meters, can't represent precise locations of features, right? It's a generalization across that entire large 10 meter by 10 meter area. You increase the chance of mixed features, like we saw with the beach and the water or the grass in the beach. We had to overlay areas, and those mixed features that might have really been to represent accurately would have shown that half the cell was one and half was the other. Now we actually mix them together and just choose one. But a large cell size obviously has a smaller file size. Imagine you're shooting with a 5 megapixel digital camera, and then you switch to a 50 megapixel digital camera, right? It's a magnitude much higher, more the pixel resolution, there are more elements to store, so the file size goes up with a smaller cell size. So again, small cell size, reducing the chance of mixed features. So if we go back to this picture here, if these were 10 by 10 meter grids and I took it down to 6 inches by 6 inches, I would have a pretty good representation of that boundary. Wouldn't have a perfect discrete line, but I'd have within 6 inches. And so I'd have a much better chance of capturing all that detail. Of course, the file size goes up when you do that, and processing time increases dramatically. We work with aerial photos from drones, and we want to get a higher resolution than the 12 megapixel uh, uh, digital still images that we can capture from our current drone. But if we go up to 20, we have to realize that the file size, the processing time for all that is going to be much greater. So those are some of the elements of raster data. Next, we're going to talk about the spectral components, the values that we get from satellite and aerial photos that are the reflectance within those cell grids. And that will be next.